the AI for Good Global Summit, convened by ITU, recognizes the joint responsibility of governments, the private sector, United Nations agencies, academia, and others to ensure AI reaches its full potential while preventing and mitigating harms.
And it's a moment that calls for action. And today I'm calling on each of you to use this summit to help the world to better understand what kinds of regulations, what kinds of guardrails we need to put in place right now. So together, let's make it innovative, let's make it safe, and let's make it responsible for all. Thank you very much.
Welcome to AI for Good, the leading action-oriented, global and inclusive United Nations platform on AI. Organized by ITU, in partnership with 40 UN sister organizations, and co-convened with Switzerland. The goal of AI for Good is to identify practical applications of AI to advance the United Nations Sustainable Development Goals and scale those solutions for global impact. In today's session, we're counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished panelists and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Hello, friends of AI, Earth, and Sustainability. I would like to welcome every one of you to a new talk in this seminar series on AI, on Earth, and Sustainable Science. You know that this seminar series in the program AI for Good of the ITU is co-convened by myself, Gustav Kamps, Markus Reichstein, Joachim Densler, and Maria Piles, and was initiated in the context of the Excellence Network ALICE for the development of AI in Europe. Well, first of all, thanks for attending the meeting today. And today we will look at an amazing topic, actually about deep generative models for molecular simulation. It is my absolute pleasure to present our speaker today, José Miguel Hernández Lobato. José Miguel is a professor in machine learning at the Department of Engineering in the University of Cambridge in the UK. But before joining Cambridge as a faculty, he was a postdoctoral fellow in the Harvard Intelligence Probabilistic System Group at Harvard University. And before that, also as a postdoctoral research associate in the machine learning group at the University of Cambridge. He basically focuses on probabilistic machine learning modeling and with a special and particular interest in deep generative models, Bayesian optimization, approximating inference, Bayesian neural networks, etc., all in place for applications in real-world data problems, and in particular for compression and molecular modeling. Well, in today's talk, we will see advanced methods in deep generative modeling for molecular simulations, also focusing on a novel approach to improve the accuracy and efficiency. Welcome and thank you very much for being with us today, José Miguel, and over to you. Really looking forward to your talk.
Great. Thanks a lot for giving me this opportunity. Let's share my slides. Good. So yeah, today I'm going to talk about this topic of deep generative models for molecular simulations. And I'm going to start with some introduction and motivation for the problem that we are going to be working with. Our goal is going to be to approximate or to model this probability distribution. We're interested in a probability distribution for the 3D atom locations. So these are the coordinates of atoms of molecules, and we call this the Boltzmann distribution. This distribution, the probability distribution, is going to tell us in what configurations the atoms of a molecule are more likely to be found in practice. So here the variable x is going to be the 3D coordinates of the atoms, and it's going to follow, these 3D coordinates are going to follow a probability distribution given by the energy of the atomic configuration. We have an energy function here, E of x, and then the probability is just exponential of minus the energy plus times some constants, okay? Why is this distribution important? It's important because it will tell us how molecules behave in the real world. It's going to tell us in what configurations we can find molecules, and it's going to allow us to answer important questions. Like, for example, is a particular drug-like molecule going to bind to a target protein or not? And there are many other applications as well, as for example, in materials design. We may want to design new materials with specific properties, and these properties may determine about the behavior of molecules. To give you an idea of how these molecules behave in time, I want to share also some simulations. So I'm going to stop sharing my slides in 1 second, and I'm going to share an animation from a simulation of molecules, okay? We will be able to see how some molecules behave in space, and this behavior is going to be given by this Boltzmann distribution. So this is a website of a company that does simulations of molecules. It's Digital Research. And here we see a very big molecule, like a protein, with some of its atoms highlighted in white color. And then we see a drug-like molecule that is also moving around it, and then we see that it binds in some region with high probability. This is a simulation that generates a trajectory of the atoms specified by this Boltzmann distribution. And we're interested in generating this type of simulations because they can tell us how molecules behave in the real world, and this is especially useful for designing new drugs, for example, and so on. Good. So let me go back to my slides, and we can think about how these simulations are actually done in practice. Okay, there are some techniques that people currently use to implement these simulations, and in particular, these techniques are called Markov chain Monte Carlo methods. Okay, our goal is going to be to generate samples from this probability distribution that will specify likely configurations of the atoms in practice. Okay, and the way this is done is by running a Markov chain, where you start your chain with a sample here, for example, with some initial value, and then you obtain a next value, and so on. You obtain different points in your chain. This chain is generated by a transition operator, where you have that xt plus 1 is sampled from the probability given by the transition operator given the current configuration for the atoms in the molecule. Okay, you run this Markov chain, and you are guaranteed that the stationary distribution of the samples in your chain is the target. Okay, this sounds great, but it's also inefficient. It's very inefficient because you need to run these chains for very long to obtain accurate samples, and this is usually expensive and inefficient. And we're going to see a different approach in this talk, where we will be able to generate accurate samples much faster. And in particular, these Markov chain Monte Carlo methods for simulating molecules have disadvantages. For example, they often are stuck into a few modes of the target distribution. Maybe your target distribution has multiple modes, maybe like this, and you initialize your chain and you generate samples maybe from this mode, but you miss this other mode. Ideally, you want to cover all the different modes in your distribution. Now, molecules, they are not going to be in a particular configuration all the time. They can be in different configurations. For example, the drug-like molecule that we found, it can be attached, or it cannot be. It can be detached from the target, and those would be corresponding to different modes or different configurations. The samples that you generate in the chain, they are correlated because you generate one sample given the previous one, and both samples are usually similar. The samples that you generate in the past are not used to improve the generation of new samples. You can run Markov-chain Monte Carlo methods for very long. You generate tons of samples. Your chain is very long, but to generate the next sample in your chain, you only use the previous one, and you ignore all the previous samples that you generated before. You only use the last sample to generate the next one instead of all the previous ones. Typically, you need small step sizes in these simulations to guarantee acceptance, and they can be very slow in practice. Typically, you need supercomputers to run accurate simulations like this for a long time. Okay. So in this talk, I'm going to tell you about a different way in which you can do these simulations. And the idea is to use generative AI, generative methods, generative models in particular. These models are going to receive as input some simple noise, like a Gaussian. For example, here we have samples from a Gaussian. And then we're going to feed them into a neural network, a very big neural network that is going to transform these samples in complicated ways. And we're going to obtain at the end an approximate distribution Q that will approximate our target distribution P. So P is the target, is this Boltzmann distribution for the 3D configuration of the atoms of molecules. It's very hard to work with it in practice, and we want to approximate it with Q. Okay. Yeah, once we have trained these models, we can generate samples very fast. You generate samples independently. You just feed noise at the input, and you get high-quality samples at the output. One thing that I forgot to mention is that the energy that we are going to be working with, this energy that determines our Boltzmann distribution, this will typically be provided to us. So someone gives us this energy function, and it's based on some physics. Okay. Typically, you will have something like a force field or even a machine learning method that gives you accurate values of these energies. And our goal is to then sample according to the probability distribution implied by those energies. Good. So we're going to focus on this approach. And you could think that this could be the future of molecular simulations. In the same way that you have seen generative AI, on the social media or so on, you usually have like a prompt like this, and then some generative AI method can generate a nice image. You have seen similar things, even with video generation, text generation, with large language models, and so on. You could think that the area of molecular simulations could be going into those directions. Maybe we have a description of the simulation that we want to implement. Maybe we want to simulate a protein with a drug-like molecule in some solvent, like water molecules. All these little points here are water molecules here. And you have like a bigger molecule, like this protein, and you want to simulate the whole thing. You could receive a description of the simulation problem, and then some generative AI method can do the simulation for you. That would be like an ideal setting. You get like a fast simulation that is also accurate. So that sounds great, but there are many challenges to implement this in practice. Okay, and for example, these generative models, these deep generative models, they are trained from energy values. We have access to this energy of the atomic configuration, but we don't have access to samples. And that's how most generative AI is implemented at the moment. All the fancy diffusion models that you see online that generate nice images, they have been trained on massive data sets of images. In our case, we don't have massive data sets of molecular configurations. We just have access to energy functions, and we have to train our models using those energy functions. Another thing is that molecules have many invariances. Okay, molecules are invariant to rotations, translations, and if we want our models to be accurate and to learn efficiently, they need to incorporate those invariances. The other thing is that molecular configurations, as I said, they are multimodal. You are going to have multiple modes in your probability distribution, molecules are likely to be in one configuration or in another, depending on the conditions, and they could change from one configuration to the other. And if we want to accurately describe these Boltzmann distributions, we have to capture these multiple modes. The other thing is that our models, they are going to be approximations of the true Boltzmann distribution, and they're going to be biased. Okay, maybe the true Boltzmann distribution maybe has a particular shape like this, and our model is more or less capturing that shape, but is having some errors. Okay, we may want to remove that bias in our models, and we'll see in this talk ways to do this. We may want our models to scale to high dimensions. We want to work with the molecules with a large number of atoms. And then we want our models to generalize across different molecular systems. If we have trained our model to, I don't know, generate accurate simulations of a particular type of molecules, when we change the molecule, we want the model to still generate accurate simulations, okay? So as I said, there are many challenges that can be quite difficult. But we are going to see how some of them can be addressed, and obviously there is plenty of research work to do in this area. So I'm going to describe briefly here some work done in my group in this area of molecular simulation, in particular done with some of my PhD students, Lawrence and Vincent, and postdocs Gregor and collaborators Bernard. Good. So. We're going to implement now this approach of using deep generative models to simulate molecules. And the first decision that we have to make when we want to implement a generative model for molecules is what generative model to use. Right now, there is a lot of options for generative models. We have diffusion models, we have variational autoencoders, we have normalizing flows, we have generative adversarial networks, and so on. There are different options. In this work, we are going to focus on normalizing flows for a good reason, but other options could be possible as well. Normalizing flows, they have one advantage, and is that they give us right away the density of the samples that they generate, okay? So in a normalizing flow, it's a deep generative model like the ones I mentioned before. You have some tractable distribution like a Gaussian here, and then you are going to feed that into a big neural network that is going to transform the distribution into something complicated. And that complicated is going to be this, the samples X are transformed into these complicated samples Y that follow a distribution that should target the Boltzmann distribution for the atomic configuration. In normalizing flows, we have access right away to the density of the samples. And this density is going to be very useful to eliminate bias in the samples generated by our model, which is going to be quite useful in practice. So the key thing in normalizing flows is that this transformation from the samples that are tractable like Gaussian into something more complicated is done using invertible functions, okay? You're going to have some invertible function, and because the function is invertible, you can right away obtain the density of the transformed sample. You have that the density of the transformed sample, the log density of the transformed sample is the log density of the original sample. And then there is this term here, a log determinant of the Jacobian of the transformation. I'm going to describe that in more detail later on. But the key thing is that we have access to densities, which is going to be useful. And we will also be able to generate fast samples. We want to generate samples fast, and normalizing flows will allow us to do that. Good. Typically, because these functions, they have to be invertible, the transformation has to be invertible, we have to introduce constraints in our neural network functions. And because of that, we may want to do multiple transformations, like not only one, but many. Yeah, and we just concatenate one transformation after the other. So in the end, we have like a big neural network given by all these sequences of transformations that results into the transformed samples. Good. So how is this density obtained? The densities are obtained very easily. You just have that if you have some particular interval dx, like this one, and you're going to be transforming it, the data points in this interval are transformed according to this transformation that is invertible. You get then that the interval dx is transformed into a new interval dy, and then the probability of finding something in the interval is the height of the density in that interval times the width. So we have this probability mass, it is this area, and the probability mass is transformed. You have this transformation of areas, and this would be the density. The height of the blue square is just the density of y. And you have that the probability mass is preserved, so the area of the blue rectangle, which is py dy, is the same as the area of the green rectangle, which is px dx, okay? And then you can solve for py. You have that py is now px dx dy, and this is the same as px dy, sorry, 1 divided by dy dx. Okay, and if you take logarithms, then you just get log py is the same as log px minus log dy dx, and this is the transformation, the derivative of the transformation, which in 1D is the same as the Jacobian. Okay, so we have this simple formula to change variables. This is in 1 dimension. In high dimensions, I'm going to skip this slide. In high dimensions, is basically the same thing, but now you will have to see how the area changes across several dimensions, and then the rectangles are transformed into these parallelograms, and the area of the parallelogram is going to be given by the determinant. So it's more or less the same. The only thing that you have now is Jacobian that tells you how the derivative, it tells you the derivative of y with respect to x. So this would be the derivative of y, which is a vector, with respect to x, which is another vector, okay? And you need to calculate the determinant of this derivative. Good. So we're going to use these normalizing flows to do our transformations. And the question is, what type of normalizing flow? What are the functions that we use in our transformations? We're going to use a flow that is very flexible, and it's called in particular neural spline flows. Okay, and the idea in neural spline flows is as follows. We are going to transform some of the dimensions of our data. So the original input x, we have this original input x, and we're going to transform it into some output y. And what we're going to do is to split x in 2 parts. We have one part here, which is x right, and x right is not transformed. Okay, it just passes right away without being transformed, and we obtain it here. So the right part of y is just the same as the right part of x without any transformation. And now the left part of x here is transformed element-wise through a transformation like the one shown in this plot. It's transformed, each dimension of x left is transformed according to this function in blue. Is just a spline transformation. Is determined by these nodes. The nodes are monotonically increasing, and that's going to be resulting into a transformation function in blue. This function in blue that is monotonically increasing. And then we just evaluate each dimension according to one of these transformations given by the nodes and the derivative of the blue function at the nodes, and we obtain the output. And that's how we obtain y left. And the key thing is that each of these nodes is parameterized by a neural network here that depends on x right. Okay? So we take X, we split it into left and right parts. The right parts are not transformed, and now the left parts are transformed element-wise through these spline transformations, whose parameters are determined by the values in X right. And the key thing with this spline flow is that it's highly flexible because of this flexibility in these transformations with the splines, but the Jacobian of the transformation is also simple. You can show that the Jacobian of the transformation is going to have some form like this. It's going to have like some diagonal, and then it's going to have maybe some non-zero entries here, and then the rest is all zeros. Okay, and the determinant of this transformation, you can show that is the product of the entries in the diagonal. So these neural spline flows are very flexible, and they can calculate determinants very fast. And we are going to be using them in our generative models for molecules. Okay. The other thing that we are going to look at is invariances. We need to know how to incorporate invariances into our model. I said that molecules are invariant to rotations and translations. And if we want to have accurate generative models of molecules, our models should capture those invariances. And there is an easy way to incorporate invariances like that into our models. And the idea is to use internal coordinates. Okay. So instead of using coordinates, spatial coordinates like X, Y, and Z coordinates to determine the position in 3D space of, we may have like the position of an atom in 3D space, maybe given by the coordinates X, Y, and Z. Instead of using these coordinates X, Y, and Z, we're going to use internal coordinates. And internal coordinates work as follows. We are going to start by placing the first atom in our molecule at the origin. So this is maybe placed at the origin always. And then we place the second atom B at distance lowercase b from the first atom. Then the second atom C is going to be placed at distance C from the second atom. And then we're going to have maybe an angle here, theta, between these two line segments. Then we're going to have another atom D placed at distance D lowercase. We're going to have another angle phi between these two segments, C and D. And then we're going to have an angle psi, which is an angle between the planes A, B, C, and the planes B, C, D. And this is a dihedral angle, okay? This is like dihedral angle. In this case, it will be psi. And given these distances and angles, we can specify the 3D location of the atoms in our molecule. And this representation of the 3D structure is invariant to rotations and translations of the molecules, of the atoms, okay? So we are going to be using it because it satisfies these properties. We have to be careful because when we operate with angles, if some of the variables that we operate with are angles, our normalizing flows, they will have to capture specific properties. And in particular, an angle of minus pi is the same as an angle of pi. This means that the density that we have, if we have in this plot density, the density at minus pi has to be equal to the density at pi. And the density at pi has to be the density equal to the density at minus pi. This means that our densities, they live in this kind of spaces like cylinders or torus or so on. And we have to introduce these constraints into our normalizing flows. Our normalizing flows, they should give us the same density when we make one angle being 0 or being 2 pi, for example, okay? If we just add 2 pi to any of the angles, then we should be able to get the same value. And it turns out that you can do this with these spline flows very easily, okay? I won't go into the details of this, but it's very easy to do that. Maybe just to give you a brief idea of what's going on. What you do is that this transformation in the spline, the derivative of the spline, if this is, for example, minus pi, if this is pi, and this is minus pi, then you just have that the densities, the derivative of the transformation here, they have to be the same, okay? And you can very easily incorporate that constraint in these neural spline flows. These are, by the way, these are 3-degree polynomials, the ones connecting the nodes, and it's very easy to introduce a constraint saying that the polynomial has to take a particular value at some input. Good, so we are going to capture those invariances by using these neural spline flows on circular variables. And now the other question that we need to address is that our models will be biased and how we can eliminate bias in our models. And this bias can be eliminated using a very simple method called importance sampling. Okay. The idea is that if you want to, for example, estimate an expectation with respect to our Boltzmann distribution of some function f of x, you can write that expectation as an integral here. And then what happens is that you may not be able to work with p directly, but you may be able to work with q. So you can write your integral now with respect to q by multiplying and dividing by q, okay? And you have this thing here now, which is an importance sampling weight. These are importance sampling weights. And you can then sample from q, evaluate f at those samples, and then reweight the samples with some weights given by these importance sampling weights. And the result is an importance sampling estimator of the quantity of interest, which is this thing here on the left. And it's guaranteed to be unbiased. Okay, on average, the estimator given by importance sampling is unbiased. The only thing is that you need to be a bit careful with its variance. But the key thing is that you can now eliminate bias by using this importance sampling. In particular, you could think about what Q is going to give you the best possible importance sampling estimator. And there is actually an optimal distribution Q to estimate the quantity of interest by importance sampling. We are going to use this later. The optimal estimator is just a distribution that is proportional to whatever you want to estimate with importance sampling, okay? It's just proportional to the product of F and P, which is what we are integrating here. And you can see that this is an optimal estimator because just with one sample, if you just use one sample, then the estimator is just F, evaluated at the sample, and then you need to multiply by the importance sampling weight, which is just Q, P divided by Q. This is the Q opt x1. And you can show that this thing here is the same as the normalization constant of the Q optimal estimator, which is just what we want to estimate, okay? So with just one sample, this optimal importance sampling estimator is going to give you the quantity of interest, and it has zero variance, which is pretty amazing. But the question is, how do you get this optimal importance sampling estimator? Because it might not be straightforward. So anyway, we're going to use importance sampling to eliminate bias in the samples. And one limitation of importance sampling is that it may fail in some settings where, for example, imagine that our distribution is, for example, imagine that our distribution is sorry, one second. Our distribution is multimodal. It maybe has two modes like this, and this would be P of X, and our approximation Q is like this, and only covers one mode. Then obviously, if you do importance sampling, you will be drawing many samples from Q, but you don't generate samples in this region. It will take you forever to generate samples in this region and cover the missing mode. So one solution to this, so importance sampling in this case is not going to work. It will give you poor estimates. So one thing that you can do to improve importance sampling is to use annealed importance sampling. And in annealed importance sampling, the idea is not to do importance sampling with respect to the target, P, but you're going to define a series of intermediate distributions, pi 0, pi 1, and so on until pi k, capital K. And you have that these intermediate distributions interpolate between the target P and your proposal distribution Q. This would be your normalizing flow Q. And you're going to do now importance sampling towards these intermediate distributions. You do a linear combination of the distributions with these coefficients beta. Beta are between 0 and 1. So when the betas are 0, you get Q, and when the betas are 1, you get P. Okay. And what you do is now importance sampling, but targeting these intermediate distributions, and that's going to be guaranteed to improve the performance of importance sampling. You do importance sampling, targeting the intermediate distributions, and also running some Markov chain Monte Carlo methods in between. I won't go much into the details of this method because it can be quite technical, but the key thing is that it's going to improve your samples. You're going to sample from Q, like this one here, but then you're going to run Markov chain Monte Carlo methods targeting intermediate distributions, and some of these Markov chain Monte Carlo methods will be able to generate samples in these other regions, okay? And that's going to allow you to cover these missing modes. And importance sampling also gives you importance sampling weights for the generated samples, which is great. We can see here how it improves things. Here, this would be the approximation Q. It's only one mode in green, and the target P has 2 modes. And obviously, if you do importance sampling in this setting, you do very poorly because you don't generate samples in regions where the target has high probability. And you have very high variance of your importance sampling weights. This is the marginal of the importance sampling weights. It has high variance. You can run an importance sampling, and in this case, you are able to generate many more samples from these regions. You improve your samples using Markov chain Monte Carlo, targeting the intermediate distributions, and then the variance of the importance sampling weights is reduced, and it works much better. So we are going to be using importance sampling to improve performance and to eliminate bias in our model. The next thing is how to train the model from energy only, okay? Recall that the Boltzmann distribution is proportional to exponential, and then we have here minus the energy, and then there are some constants here, times some constants, okay? And we are only given access to this energy. So how do you train your model from energy functions and not data? One thing that you can do could be to minimize a divergence between your generative model distribution Q and the target Boltzmann distribution P, like this Kullback-Leibler divergence, which has this formula. And this would be something that you could do. You could optimize this using numerical optimization methods. But this doesn't work in practice, unfortunately. It doesn't work because if your target has many modes like this one here, this objective, this Kullback-Leibler divergence objective, it's mode seeking, and it will only fit well a subset of the modes like these ones, and it's going to fail to cover the other modes. And the reason it fails to cover the modes is because this log density ratio between P and Q represents the error. If P is the same as Q, the ratio is 1, the log of 1 is 0, so the error is 0, and you're happy. But in regions where P is not the same as Q, this will be non-zero, and then you will have high error. But this error is weighted by Q here. So in these regions, the density of Q is very low. And even though the error is high, because the density of Q is low, I don't care about that with this objective. So this objective will be mode seeking, and it's going to fail in complicated problems where the Boltzmann distributions are multimodal, okay? So what we are going to do is to use a different divergence to feed our flow. We're going to use something called the α-divergence, which is proportional to this integral, where we have now the density ratio between P and Q here, but raised to this power alpha, okay? And we calculate the average with respect to Q. And for different values of alpha, you can go from mode-seeking behaviors like alpha, large, and negative, with your approximation Q, which is only a Gaussian with only one mode. Here, P is bimodal and it has two modes. When alpha is large and negative, then you are mode-seeking and you fit only some of the modes. And if alpha is larger and positive, you tend to do mass cover to cover all the mass of the target. Okay, we're going to use alpha larger, not very large, but larger than 0, and that's going to produce mass covering behavior that fits all the modes. And you can also show that this alpha divergence with alpha equal to 2 is related to the expected value of the squared of the importance sampling weights. And that's going to be related to the variance of the importance sampling weights. So this is another advantage of this method, because it will allow you to minimize the variance of the importance sampling weights. So you're calculating, for alpha equal to 2, here is just the integral, and then you have the importance sampling weight here raised to the second power, and you calculate the average with respect to Q. Okay, so this is the expected squared in importance sampling weights, and that's going to be minimized when the variance of the importance sampling weights is as small as possible. So by minimizing this divergence, we cover all the modes, but we also minimize variance when we do importance sampling. And we will be doing importance sampling to remove bias in our generative model. So we can then use this method. And the key question is, how do you minimize this divergence? Because it's not straightforward how to minimize the alpha divergence. And what we are going to do is to use the optimal importance sampling distribution to estimate the divergence. Okay, the divergence has this formula with alpha equal to 2, and you need to solve this integral. And we know that the optimal importance sampling distribution is going to be proportional precisely to whatever you want to integrate. That's what we saw before. And this is going to be our optimal importance sampling distribution. It's just P squared over Q. If we want to estimate the alpha divergence with an optimal importance sampling distribution, that distribution is proportional to P squared over Q. And you can then calculate gradients when you use this optimal importance sampling distribution. And the interesting thing is that you have a very nice formula for the gradients. The gradients are as follows. You will need to sample with respect to the optimal importance sampling distribution, P squared over Q. And then you evaluate the likelihood of the flow, and you maximize this. And this is the best way to make your flow cover all the different modes. Because what you are doing is you are sampling from P squared over Q, which is high in regions where you miss probability mass. You can see it in this example. This is P here. And then we have this approximation Q, and Q is missing mode, it's missing mass in this region. And to minimize the alpha divergence, what you are going to do is to sample from P squared over Q, which is here in green. That samples from regions where we miss probability mass. And then we are going to maximize the flow likelihood with the generated samples. We are going to make the flow have high probability mass in that region. This is what we do to train our flows. We are going to sample from the optimal importance sampling distribution, P squared over Q. We do that using an annealed importance sampling, targeting P squared over Q. We get importance sampling weights, and then we evaluate the log likelihood of the flow on the generated samples, and then we try to maximize that likelihood. And this works way, way much better. I'm going to skip this slide because of the lack of time. And the other thing is that because we train our flow by sampling with an annealed importance sampling from this distribution, P squared over Q, that can be expensive, and we don't want to waste compute effort by throwing away our samples. So we are going to sample from P squared over Q. We're going to use those samples to update our flow by maximum likelihood. But then we don't throw away the samples, we keep them in a buffer. And then we are able to resample from this replay buffer. We keep the samples in a replay buffer, and we just keep resampling from the replay buffer, updating our flow. and then generating new samples and putting them in the buffer. Okay, and then the old samples, we can throw them away, and that speeds up quite a lot of things. I'm going to skip that and then show some results on some interesting problems. This is the multiple modes mixture of Gaussian problem. We have a flow that is initialized quite narrowly. If you minimize the Kullback-Leibler divergence, you miss all the modes. This is what our method does, training only from the energy values. And by just targeting this p²/q and generating samples from regions where we missed probability mass, and then using those samples to update our flow to try to increase the probability mass of the flow there. And we see that we are able to cover all the modes, and we obtain very good results. We tested our method to simulate this molecule, the alanine dipeptide. This is used as a benchmark to evaluate the quality of methods of generative models for simulating molecules. And this is a molecule that is more or less, so the atoms have rigid connections, but you have these dihedral atoms, angles, phi and psi, that have more variability. And you see here the 2D histogram for the probabilities that values that those angles can take. The angles go from -pi to pi, from -pi to pi. And we see that values at -pi here are the same as those at pi here, the same as here, and here as well. These values are the same, okay? So these ones here, they are the same. This is the ground truth histogram obtained with a very expensive simulation run to simulate this dipeptide. And this is what you obtain if you train a flow by maximum likelihood on ground truth samples, and then you sample from the flow, you will get this histogram. This is what you get with our flow, with our method. It's not using ground truth samples, it's just generating samples from p²/q using annealed importance sampling. And it's overestimating the probability mass in the tails in these regions. Here, for example, you overestimate a bit probability mass. But the reason for this is that this flow, then you can do importance sampling to reweight your samples, which is what we do in this plot. And we see that this plot, when we reweight our samples with importance sampling, is indistinguishable from the ground truth one, okay? And this is actually the first time that someone was able to generate this type of accurate results in this dipeptide problem. So we also look at something like the effective sample size of the reweighted samples that we obtain with our flow, and it's very high. It's almost close to 100%. And this is even higher than with a flow trained by maximum likelihood on ground truth samples. And you can look at the distance metric with respect to the target. And our model has a smaller, distance metrics than a flow trained on ground truth samples by maximum likelihood, which is pretty impressive. So just to conclude, this method, I have described this method FAB. It's a method that allows you to cover multimodal distributions, training only from energies, and it uses these key ingredients, α-divergence, minimization, annealed importance sampling, bootstrap training, a replay buffer, and so on. It only requires the target density or the target energy, but no samples from the target. And we obtained really amazing results on this alanine dipeptide problem. To conclude, I also want to remind you of the challenges in this area. I have shown how to address some of these challenges, but there are still many remaining ones. We want to train deep generative models from energy values and not only from samples. We want to encode imbalances into our generative models. We want to be able to feed multimodal Boltzmann distributions accurately. We want to remove bias in our models, scaling these models to high dimensions, and we want our models to generalize across different molecular systems, which is quite challenging. Good. So I think, yeah, that's been all. And thanks a lot. I think we may have now time to address some questions. Is that right?
Yes, I think so. Thanks very much, Jose Miguel. Thanks for this very informative and very motivating talk. Well, I'm pretty sure there will be some questions and doubts or curiosities or whatever in the chat. But in the meantime, maybe I don't know. While people is warming up, I have some little questions and curiosities myself. So you mentioned at the very beginning that these two fields of molecule design, or or what you have been presenting, and also material sciences are kind of connected, no? I mean, they are share many similar challenges.
Yeah.
But I don't know a word about this, but maybe there are also some commonalities in terms of methods and approaches, or
Yeah, that's right. I mean, this area of machine learning for molecules is exploding in the last few years, and there are many techniques that are used across different settings. This drug discovery is one area where people use these methods quite a lot, but materials science is similar. In these problems, maybe you want to predict properties of molecules. You may want to generate new molecules that may have some particular properties, and then you will be using generative models for that. You may also want to simulate how the molecules would behave. Maybe I mean, I'm not an expert in this area because my expertise is more on the machine learning side, but in the area of materials, for example, something that is quite relevant at the moment could be catalysis, where you maybe want to design new ways to perform chemical reactions in a cheaper way, for example, for converting carbon dioxide into something else or so. And then I can imagine you could do simulations of accurate simulations of molecules to know exactly if these reactions are going to take place or not.
Yeah. I think that there is like this fruitful collaboration across both methods and applications, I think. And we have seen this, cross-sectional applications all over the place in this seminar series. People working with remote sensing data that they take this method and apply to climate sciences and vice versa, and this and that. No, it's very nice that what you mentioned. I'm now a bit more intrigued about maybe becoming a bit more technical about the extrapolation capabilities, no? About the methods that you've been using. No?
Yeah.
Because you said for the very beginning, you just admitted, okay, I will have only the prescriptions, let's say, for the energy, but I don't have data, right? And now I'm a bit puzzled and concerned, right? Because if you're not learning from data and you are only learning from a prescribed energy, you will never be able to extrapolate, right? Or maybe I'm missing something here. Or maybe it's just that Boltzmann sampling does the magic. I don't know.
Yeah, I mean, you will have to introduce some constraints into your problem. For example, in the dipeptide, sorry, I'm going to show this here. In the dipeptide, this molecular configuration is not the lowest energy one. Okay, the lowest energy one probably is just with this dipeptide broken into maybe water and carbon dioxide molecules. Okay. And we are introducing some constraints into the model by saying, we introduce some constraints into the model by saying that the bonds have to be satisfying a particular value for the distance. Okay, we don't let the molecule break.
Yes,
we wanted to say that because actually, if you generated samples, then the most likely samples that you will be eventually getting is these low energy configurations where the dipeptide is broken and it's separated into water or so. What happens now is that here we're in a particular mode of the configuration of the atoms, which corresponds to the dipeptide, and we don't let our samples escape that mode. Yeah. I can also say something quite interesting on this project. We implemented this method and we tested it on the dipeptide, and it was not working. We were comparing the samples that our method was generating with ground truth samples generated with molecular dynamics simulations, and they were different. And we were puzzled why they are different. Everything in our method seems to be fine. And it turns out that this dipeptide, it's a chiral molecule, which means that chiral means that you can create the same molecule, exactly the same, but by where you invert some of these bonds, you kind of invert the bonds so that the molecule is a mirror copy of itself, but it's different. And this represents two different modes of the molecular configuration. You have the dipeptide as it is, and the mirror image of the dipeptide. So our method was generating samples from both modes. It was able to generate samples from the dipeptide and the mirror image, but the molecular simulation samples that we had generated with molecular dynamics methods, they were not able to escape the original mode for the dipeptide. So we were comparing our method that was sampling from the two modes, both mirror images of the dipeptide with only the one only of the images, and obviously the samples were different. So in that sense, we are kind of manually constraining the system so that we only sample from specific configurations. Okay. And if you had different molecules, then you will have to introduce these constraints. Say, maybe I want to sample this molecule, and I know that now there are these bonds. And then I'm going to give some flexibility between the bonds, but I don't let the atoms move maybe much farther away than what I expect. And then you would expect that your method should be doing a good way in that case. This method, right now, it only works on the dipeptide. It's not able to generalize, but the ideal setting is that now you don't consider only one single molecule, but you consider many different molecules. Yeah. And you might be able to learn conditional generative models.
True. That brings me to this question of, okay, you're kind of, I mean, you said so, right? To include some kind of invariances, right? Or try to encode in, at least in the representation, I think.
Yeah.
But I guess that the other prior or other constraints could be introduced or are useful, right? I don't know. I'm thinking of, energy stability or any conservation law maybe or something like that. I don't know if the people in the field is...
Yeah, that's a very good point. One of the things that we are considering more recently also is that we have access to this energy function. We have access to the energy of the let me see, in the we have access to the ground truth energy. So we have access to these energies. And these energies, sometimes they are given by machine learning methods as well. So these are machine learning methods that are implemented based using a bit of physics inspiration. And they could be like a type of neural network. And the question is, if we have a neural network that gives us the energies, and that neural network uses maybe some feature representations, maybe you could use those feature representations also in your model. And that could also be beneficial for learning. I don't know, it's something that you could consider.
But you could also implicitly using them as well, right? I mean, if you're using the energy given by these models, you're already...
Yeah, I mean, we use the energy values, but we don't use the features that are used to calculate the energy. So it's slightly different, but you could maybe think about introducing some structure into your generative models that is specific of the problem. I mean, this thing with the imbalances is one way, but there could be other things. And I don't know, I mean, I think this is an area where there is plenty of potential for creating more accurate models. And I think people are only starting to scratch the surface.
True. That reminds me again back to my previous question. I mean, the first question on material science, that they try to incorporate, stability or symmetries or these kind of things, right? So maybe there's...
Yeah, that's right. Yeah, so in materials, for example, you have quite a lot of these symmetries. I mean, you would have like some, I don't know, element that is repeated many times or so. And I can imagine that you could incorporate those into the models. If you have a generative model for materials, I mean, some people, they have worked in this area and they have tried to incorporate these symmetries. And you could you could think of doing something similar for molecular simulation as well. If you know that there is some regularity or periodicity or so, you could also incorporate it into your model.
Good, good. I think that we are running out of time. I just finally have a very maybe a bit technical question about you emphasize the role of the functions or the links, right, in your invertible neural network normalizing flow, let's call it. And you said, okay, spline transformations are cool because of this or that, right? But it is more about, I don't know, I want to know basically if it is more about the advantage of a speed up or tractability, or because there are so many, right? I mean, there are plenty of flows.
Yeah, so there are many types of flows. That's right. The question is why maybe splines, no? Is that?
Yeah, exactly. I mean, we are playing a bit on this, and you know, it's.
Yeah, so one of the things is that, for example, our method is based on running. I mean, you need to sample from this p squared or over q.
Yes.
And the way we do that is we sample from q, and then we run an idempotent sampling targeting p squared over q. This means that you need to be able to sample from your model, and you need to be able to evaluate densities fast. So we want something where you can sample fast, you can evaluate densities fast, and these coupling flows that have this particular transformation where you split the data into two parts and one is transformed as a function of the other. These are coupling flows. They are very fast. So they will allow us to generate samples very fast, to evaluate densities very fast, and that's why we use them. You could use other more complicated flows like continuous normalizing flows. No, people use also continuous normalizing flows. They are quite flexible, but they are way slower to generate samples and to evaluate densities, and that's why we don't use those.
Yeah. But in the end, there are not that many examples, right? I mean, the computational cost of running it is not that high, no? I guess, no, because at least for the validation, I don't know. I mean,
I mean, for the validation, at least we compare with using the samples. And for example, in these results that we have, I mean, we don't have results on the computational cost. But for example, at the end, we compare with fitting flows by maximum likelihood on ground truth samples, and the time that it would take you to generate the ground truth samples will be quite high. So we use way fewer samples. Maybe we don't have results in terms of time, but once imagine that you have already trained your model, then generating independent samples is extremely fast.
Yes.
So once we have trained our model here, then you just generate the samples super fast. And if you wanted to generate independent samples, then you will have to still run your chain for very long. So in that case, it would be like way faster. But training the model can also be slow. So you have to be careful with that.
Yes. Other let's say Monte Carlo approaches, because maybe, I don't know, I was just thinking.
People will use parallel tempering or
calls in the distribution, right? Or I don't know.
Yeah, the state of the art to generate these samples would be to run parallel tempering or replica exchange, and you run chains at different temperatures, and you allow the samples to change from those. Those would be kind of the state of the art sampling based method. Nice.
Yes. Wow, this field offers so many possibilities. It's really amazing. I mean, challenges, right? I guess. I don't know. According to your expertise, what do you think would be the most challenging thing? I mean, associating these two other fields, or just
I think scalability
to other molecular systems or something like that.
Scalability to higher molecules, to big molecules, is one of the most challenging ones, because you need to work with many atoms, and then the dimensionality just increases a lot, and then it's hard to. I mean, you will need a lot of compute. I think my expectation is that we will see bigger and bigger models in this area that are working out on larger scales. And maybe in the same way that we have seen these advances in large language models, we will see now advances in generative models for molecules that will become bigger and bigger. And then have a higher and higher accuracy.
Yes, very, very nice. So let me just check if there are questions here in the chat. Apparently there is none. So I guess that maybe we could no questions. Okay, so maybe we can just finish here. I think it was a great discussion and a
Good.
fantastic talk.
Yeah, thanks a lot.
So yeah, very much. Thank you very much, Josemira, because because of presenting and going in details of the methodologies and the application. Now I think it's time for closing the session, and thanks again for your talk and all the attendees, and thanks for staying with us. And remember that you can still continue conversations if you wish in the neural network area. If you're registered, of course, and that is also a very good opportunity to follow up with any questions that are pressing now. We hope to see you in our next talk in our seminar series on AI for Earth and Sustainability Science. Thanks, everyone, and have a good day.
Thank you. Bye. Bye-bye.
Thank you for participating in today's AI for Good session. We hope you've learned something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. We invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the eShop, and build your personalized AI for Good program. Let's shape the future of AI for Good.
The AI for Good Global Summit, convened by ITU, recognizes the joint responsibility of governments, the private sector, United Nations agencies, academia, and others to ensure AI reaches its full potential while preventing and mitigating harms.
And it's a moment that calls for action. And today I'm calling on each of you to use this summit to help the world to better understand what kinds of regulations, what kinds of guardrails we need to put in place right now. So together, let's make it innovative, let's make it safe, and let's make it responsible for all. Thank you very much.
Earth.